This is lesson 7.3 Symmetric Matrices and Orthogonal Diagonalization. Believe it or not, this is our very last lesson for this series, our very last lesson for this class. I kind of feel like we need a moment. Okay, great. Let's move on. We have not gone gentle into that good night with this chapter. We've had two big lessons already in 7.1 and 7.2, and we are ending with quite a doozy. This is a big lesson. There's a lot in here, and we're gonna finish strong at the very, very end with a really big example. So buckle in, hang on tight, because here we go. We're gonna start off with the definition of a symmetric matrix, which simply says that a square matrix is symmetric when it is equal to its transpose. In other words, if I just took a 3x3 matrix, and let's just make it look something like this, and you'll notice even as I'm filling it in, I'm being kind of intentional about how I fill it in, because by definition, if I look at this matrix, I will notice that row 1 and column 1 are the same, row 2 and column 2 are the same, row 3 and column 3 are the same. The matrix is equal to its transpose. Another way to see this, though, is simply by inspection. If I look across the main diagonal, this to be symmetric, this matrix has to be symmetric across that main diagonal. So it's a mirror image where I have a 0 and a 0, a 4 and a 4, a -1 and a -1. Okay, so you can kind of see it by inspection, but mathematically, matrix is equal to its transpose is what makes it symmetric. Which leads us to our first theorem in this lesson, properties of symmetric matrices. So if we have a square symmetric matrix, then these three things are true. First of all, the matrix A is diagonalizable. Secondly, all of its eigenvalues are real, so no non-real or imaginary eigenvalues. And 3, if lambda is an eigenvalue of A with multiplicity k, then lambda has k linearly independent eigenvectors. That is, the eigenspace of lambda has dimension k. Now, we've seen all of these concepts before, so this is what would then be specifically true if the matrix is in fact symmetric. And then this is not a theorem, this is just almost kind of the antithesis of what we just talked about for non-symmetric matrices, things that could be true about a non-symmetric but would not be true about a symmetric. So non-symmetric would not be or may not be diagonalizable. It could be, but not necessarily. Does not have, or excuse me, can have non-real eigenvectors. They could be real, they could be non-real, they could be a mix of both. And the number of linearly independent eigenvectors corresponding to an eigenvalue can be less than the multiplicity. So if it's symmetric, it has to be equal to the multiplicity. If it is non-symmetric, it may or may not be. It could be equal or less than the multiplicity. All right. So our first example, we're not actually going to, we're going to prove something. We haven't done a lot of proofs in this class, but I thought this would be a good proof to look at. It says prove that a symmetric matrix A given by ACCB is diagonalizable. So what we're going to do is like always, we're going to find the characteristic polynomial and use that to investigate the eigenvalues. Now, in this case, we have letters, not numbers, so we won't be able to actually find the eigenvalues, but hopefully through the process of finding the characteristic polynomial, looking at what its roots might be, we'll be able to infer some things about those eigenvalues. So let's start by finding that polynomial, so lambda I minus A. So in this case, we're just going to take lambda minus A, negative C, and lambda minus B. And if we simplify that out, we're going to have lambda minus A, lambda minus B, minus C squared, which is lambda squared, minus, now we're going to have a minus A lambda and a minus B lambda. I'm going to factor out the lambda and write this A plus B lambda and then minus C squared. Because I want this in standard form. Oops, I'm actually missing a term here, aren't I? Because we'd also have a plus AB at the end of that. So we'd have a plus AB and then minus C squared. So I want this to be in standard form, where basically our A is 1. This would kind of represent our B, and this would represent our C if we're thinking about standard form of a polynomial. So now we want to find the roots. Again, we're not going to be able to find actual roots, and we certainly can't factor this, but we could use the quadratic formula. So if you think about the quadratic formula, remember that's the negative b plus minus square root b squared minus 4ac all over 2a, okay? I want to focus in on the discriminant of this formula because the discriminant tells us things about the roots, right? Obviously, if that discriminant is negative, we have imaginary or non-real roots. If it's 0, we have exactly one root, negative b over 2a. And if it's greater than 0, we have two distinct roots. So we're going to use that discriminant on this polynomial to see what kinds of eigenvalues we might have. So b squared is going to be a plus b squared. Obviously, it's minus, but we don't need to worry about the negative because we're squaring it anyway. And then minus 4 times a is 1, times c is ab minus c squared. All right, let's simplify this out. So again, this is the discriminant that we're finding here. I'll write that out. So just to remind us of that. So we're going to write a squared plus 2ab plus b squared minus 4ab plus 4c squared, which is, let's see here, 2ab minus 4ab. So we're going to write a squared minus 2ab plus b squared plus 4c squared. And this part right here can be factored. And this is going to be equal to a minus b squared plus 4c squared. All right, so that is our discriminant. And if we look at that, we've got two things that are being squared and added together. So obviously that can never be negative. So we don't have any non-real zeros. But we do have two possibilities, right? One possibility is that it could be 0. It is possible for that discriminant to be 0. But in order for that to happen, a and b would have to be equal. So when you take a minus b, you get 0 squared. And c would have to also be 0 as well. So obviously 0 squared times 4 would be 0. You'd have 0 plus 0 is 0. So in this case, what would happen then is if a and b are the same and c is 0, a is already diagonal. Because if we go back to our original matrix, if a and b are the same, we can just call those both a, and if c is 0, you'd have 0 and 0, and that's a diagonal matrix. All right. The other situation is the case where that discriminant is greater than 0. But if it's greater than 0, that tells us that a has two distinct roots and real roots. So then a has two distinct real roots. And if we have two distinct real roots or two unique real roots, then a has to have two distinct eigenvalues and is therefore diagonalizable. Okay, so therefore a has two distinct eigenvalues and is diagonalizable. Again, diagonalizable because, sorry, I can't write that. I can never spell that word and talk at the same time. It's diagonalizable because it's a matrix of order 2 by 2, and it has two distinct eigenvalues. That tells us that it has to be diagonalizable. All right, so that's the proof. All right, well, let's move on and let's do an example where we're actually going to find the eigenvalues of a symmetric matrix. And in this case, then we'll also determine the dimensions of the corresponding eigenspaces. So again, we're going to start by finding that characteristic polynomial, use it to get our eigenvalues, and then once we have the eigenvalues, we can talk about dimension. So in this case, we've got the discriminants of lambda minus 1, 2, 0, and 0. 2 lambda minus 1, 0, 0, 0, 0, lambda minus 1, and 2, and then 0, 0, 2, and lambda minus 1. Now, unfortunately, we don't have a row or column with 3 zeros. The best we can do is 2, so we'll have 2 parts to this that we'll have to look at. So I'm just going to start up here with lambda minus 1. So we'll have lambda minus 1 times the discriminant of kind of that lower right corner, which is lambda minus 1, 0, 0, 0, lambda minus 1, 2, and 0, 2, lambda minus 1. And then I'm going to go across to the next 2, so minus 2 times the discriminant of, I'm going to do the columns this time, it's a little bit easier. So 2, 0, 0, 0, lambda minus 1, 2, and 0, 2, lambda minus 1. All right, so simplifying that, for the first part, we'll have lambda minus 1. And then here, to find the discriminant, we'll just focus on that lambda minus 1. So we'll have lambda minus 1. And then times the discriminant of this part, which is lambda minus 1 squared, minus 4. And then we've got the next part of the problem. We've got the minus 2. And then times, again, I'll just focus on that 2 because the rest are zeros. 2 times lambda minus 1 squared minus 4. All right, so doing a little bit of simplifying here, we've got lambda minus 1 and then times lambda minus 1. And then this whole thing in brackets simplifies out to lambda squared minus 2 lambda plus 1 minus 4 is minus 3. And then minus, we can multiply the 2's together, so 4. And then again, let's simplify that inside. It's actually the same one as before. Lambda squared minus 2 lambda minus 3. Okay. So if we factor out, notice we've got these two are the same. So I'm going to factor those out and write lambda squared minus 2 lambda minus 3. And then what I have left is this piece and the minus 4. And I'm actually going to multiply that out right away. So I've got lambda squared minus 2 lambda plus 1 minus 4 is minus 3. We get the same thing. So this factors, one of these factors, lambda minus 3, lambda plus 1. So obviously the other one factors the exact same way. So what we end up with is lambda plus 1 squared and lambda minus 3 squared. So this whole thing boils down to that. And what that tells us then is we have 2 unique eigenvalues. We've got one, which is negative 2, has multiplicity 2. And then we've got another one that is equal to 3, also with multiplicity 2. So again, kind of going back, if an eigenvalue of A has multiplicity k, then the eigenspace has the same dimension. So in this case, we have multiplicity of 2. So both of these have dimension 2. All right. Now, if you want to know what they are, obviously we could go on and we could find the matrices and go through all of that. I'm going to just give you these just so you have them. If you want to take the time and actually calculate or find these eigenvectors, but the eigenspace of lambda 1 equaling negative 1 has a basis of B1, which is equal to 1, 1, 0, 0 and 0, 0, 1, 1. So those would be the 2 vectors in the basis, which gives it dimension 2. And then for lambda 2 equaling 3, it has the basis of B2 given by 1, negative 1, 0, 0 and 0, 0, 1, negative 1. So again, 2 vectors, dimension of 2. If you want to take the time to go through and calculate those, verify that those are actually the bases, you are free to do that. All right, but let's move on here. And let's go on to the definition of an orthogonal matrix. So we've talked about symmetric matrices. Now let's talk about orthogonal matrices. We've talked about orthogonal vectors before, so that may sound familiar, but now we're obviously dealing with matrices. So it says a square matrix P. That's the same P in the formula down here, the P inverse AP. That square matrix P is orthogonal when it is invertible and its inverse is equal to its transpose. Okay, so its inverse is equal to its transpose, then it is orthogonal. So show that the matrix P is orthogonal by showing that its inverse is in fact equal to its transpose. So in this case, what we're going to do is let's start by finding the determinant of P. The reason I want to find the determinant of P is to help us find the inverse. Determinant of P is 0 minus a negative 1 is plus 1 or just 1. So remember, in a 2 by 2 matrix, you can find its inverse by just multiplying switching the diagonals along the main diagonal and then changing the signs of the other two. But if the determinant isn't 1, you have to multiply it by 1 over its determinant. So that's why I wanted to find its determinant. So in this case, it's inverse. The zeros stay where they are. The ones change signs, and that's our inverse matrix. The transpose, row 1 becomes column 1, row 2 becomes column 2, and these are obviously the same matrices, therefore P is orthogonal. So that's all there is to it, just showing that its inverse and its transpose are the same. You could obviously just use a calculator, especially if this is a 3 by 3 or a 4 by 4. I would just plug it into a calculator, calculate the inverse, calculate the transpose, see that they're the same. You know that they are that it's orthogonal matrix. All right, so then we've got a theorem related to the property of an orthogonal matrix, and it says an n by n matrix P is orthogonal if and only if its column vectors form an orthonormal set. All right, you may remember orthonormal. I think this was back in chapter 5 that we talked about this. There were two conditions in order for something to be orthonormal. The first is that again, we talked about this in the terms of vectors, but now in terms of matrices, the matrices have to be mutually orthogonal, and they have to be unit vectors, unit vectors, because we're talking about the column vectors here, so unit vectors. In other words, they have to have a length of 1. Okay? So we're going to show that the following matrix is orthogonal by showing that P inverse is equal to this transpose, and then showing that the column vectors of P form an orthonormal set. So again, talking about vectors, that they are mutually orthogonal, which we would do in the first part, and then just showing that those vectors have a length of 1. All right, so the way that we can do this, because again, we could toss this into our calculator, we could find the inverse that way. But the other way to do this is if I take P and I multiply P by its transpose, what I should get is the identity matrix. Because if I get the identity matrix, that tells me then that P transpose and P inverse are the same, because P times its inverse should give me the identity matrix. So in this case, if this happens, if I get the identity matrix here, that tells me that these two things have to be the same. So that's how I'm going to go about finding this or showing this. So I'm going to take this big matrix. I'm not even going to rewrite that thing. We're going to take that matrix and we're going to multiply it by its transpose. And that one I will write out. So its transpose, row 1 becomes column 1. Row 2 becomes column 2. 1 over root 5 and 0. And row 3 becomes column 3. Negative 4 over 3 root 5 and 5 over 3 root 5. Okay. Now, again, if you want to do this on a calculator, plug it in there, that's fine. If you want to do it by hand, either way. I will tell you that, in fact, it does equal the identity matrix. And therefore, that tells me that P inverse is equal to the transpose. So then it's orthogonal. And now we have to basically show that the column vectors have a magnitude of 1. I'm sorry, this doesn't show yet that it's orthogonal. The orthogonal, we showed that the matrix is orthogonal. So that's the first part. So we did this part. Now we need to show that we have an orthonormal set. So we have to do mutually orthogonal again, but not for the matrix. Now we're going to do mutually orthogonal for the vector columns. Okay, so there's two ideas going on here with kind of this orthogonal for the matrix, but now orthogonal for the column vectors. So I'm going to go on here, and so basically we have that the 3 column vectors are just these right here, right? These are column vectors. Wait, I'm sorry, that's the wrong matrix. Column vectors are up here, right? So we've got these 3 column vectors. So 1/3 -2 over root 5 and -2 over 3 root 5. And then we've got a second column vector of, what do we have here? 2/3 positive 1 over root 5 and -4 over 3 root 5. And then our third column vector is 2/3 0 and 5 over 3 root 5. Okay, so these are the column vectors that we need to show now are mutually orthogonal, that each one of these is orthogonal to the other, and that they are unit vectors. Okay, now again, I'm not going to go through the actual math of this. If you want to verify this, you can, but bottom line is we need to show that the dot product of P1 and P2 is 0, which would be the same as the dot product of P1 and P3, which would be the same as the dot product of P2 and P3. So if you take all combinations of 2 vectors and find their dot products, all 3 of those need to have a dot product of 0. That's going to tell us that they are mutually orthogonal. And again, I will tell you that they are, that if you were to do those dot products, you will get 0. Excuse me. And then we need to show that they're unit vectors. So that just means that their length is 1, so we just need to find their magnitudes. So magnitude of P1 has to equal the magnitude of P2, has to equal the magnitude of P3, all of those equaling 1. That would tell us that they are unit vectors. And as long as both of these things are true, mutually orthogonal and unit vectors, which they are, we know that these column vectors P1, P2, and P3 create an orthonormal set. Is an orthonormal set. Okay? So 2 ideas. Again, just one is just simply showing that the matrix itself is orthogonal by showing that P inverse is equal to its transpose. And then the other is showing that the column vectors form an orthonormal set by showing that those column vectors are mutually orthogonal, that they're orthogonal to each other, dot products are 0, and that they are unit vectors, that their lengths are 1. All right, moving on. We've got another theorem here. So the properties of symmetric matrices. Let A be an n by n symmetric matrix. If lambda 1 and lambda 2 are distinct eigenvalues of A, then their corresponding eigenvectors, x1 and x2, are orthogonal. All right, so show that any 2 eigenvectors of A equaling 3, 1, 1, 3, corresponding to distinct eigenvalues, are orthogonal. So let's go ahead and let's actually find the eigenvalues for this and then get the eigenvectors from that. So in this case, taking lambda I minus A, discriminant of that is going to be the discriminant of lambda minus 3, -1, and lambda minus 3, which is going to be, I'm just going to multiply this out right away. We'll have lambda squared minus 6 lambda, And then we'll have a plus 9 minus a 1 is a plus 8. And that factors lambda minus 4 and 2. So lambda minus 2, lambda minus 4. So in this case, we get two distinct eigenvalues. We get one equaling 2 and the other one equaling 4. All right, so now when lambda is 2, we're going to find 2i minus a. So plugging in 2 is just going to give us negative 1, negative 1, negative 1, and negative 1. Remember, we always want to put these into reduced row echelon form. And if we do that, that gives us the matrix 1, 1, 0, 0. So x1 plus x2 is 0, telling us that x1 has to be equal to negative x2. So in this case, then x1, if I let x1 be s, then x2 would be negative s. And then likewise, when lambda 2 is 4, we'll have 4i minus a. So plugging in 4, that's going to give us the matrix 1, negative 1, and negative 1, 1. And again, row reducing gives us the matrix 1, negative 1, and 0, 0. So here, we basically have x1 equals x2. So x2, if I let x1 be t, x2 is also t. All right, so we've got our x1 and our x2. And again, we need to show that these are orthogonal. To show that they're orthogonal, we need to show that their dot product is equal to 0. So I'm going to take the dot product of x1 and x2. So s times t plus a negative s times t is minus s times t, which in fact is 0. And therefore, x1 and x2 are orthogonal. Orthogonal. There we go. All right. All right, moving along. I know this is a lot of material and I'm going fairly fast, but again, you can always go back and rewatch if you need to get a little more digestion on some of this stuff. But let's get into orthogonal diagonalization, the whole kind of one of the big points of this lesson. It says a matrix A is orthogonally diagonalizable when there exists an orthonormal matrix P such that P inverse times A times P equals a matrix D that is diagonal. Okay? And the theorem then that follows is if we have a square matrix A, then A is orthogonally diagonalizable and has real eigenvalues if and only if A is symmetric. Okay, so that theorem almost kind of trumps the definition above it, because what that says then is if we know that A is symmetric, we know that it has to be orthogonally diagonalizable. Okay, so that's typically what we're going to look for. And so in this case, in our example, which matrices are orthogonally diagonalizable, and remember, this is an if and only if statement, so it has to go both ways. It is only orthogonally diagonalizable if it is symmetric, if the matrix is symmetric. So in this case, A1 is symmetric, A2 is not, A3 certainly is not, and A4 is. So the only two that are orthogonally diagonalizable, this is a tongue twister of a lesson, are A1 and A4. All right. So how do we actually find a matrix that would be orthogonally diagonalized to another matrix? These are the steps that we have to go through. And this is going to lead us into our final example, our very, very last example for this class. But I'll tell you what, it's a big one. So we're going to have fun with this. But these are the steps we have to go through. So first of all, we're going to find the eigenvalues like we always do using the characteristic polynomial and determine the multiplicity of each. Then for those with multiplicity 1, we're going to find the unit eigenvector. Obviously, if it has multiplicity 1, there's only one eigenvector. And then once we find that, we're going to normalize it. We're going to transform it into a vector of length 1. Then for anything that has multiplicity greater than or equal to 2, we're going to basically do the same thing. We're going to find the set of linearly independent eigenvectors. If it's not orthonormal, we have to jump back to something we did in Chapter 5, the Gram-Schmidt orthonormalization process, and use that to basically make them orthogonal. And again, normalize them. And then once we have all of those eigenvectors, we're going to put those into column vectors to create the matrix P. All right. It's a lot of work. I'm not going to lie. It's a lot of work to do. We're going to do an example, and this is a huge example. It's going to take us about 1.5 pages to 2 pages to do this. But we're going to walk through all 4 of these steps. And so I'm going to walk this through, and we're going to do this. So find a matrix P that orthogonally diagonalizes A, the matrix given by the following. Okay. So step 1, find all of the eigenvalues of A and determine the multiplicity. So this is what we've been doing pretty much this whole chapter. We're going to find the characteristic polynomial, and we are going to then use that, find the multiplicity of that once we get the eigenvalues. Part of what makes this actually a difficult problem is if you look at the matrix, there are no zeros in it. So finding the determinant is actually a bit of work here. In hindsight, maybe I should change this to a bunch of zeros to make this a lot easier. But you know what? It's our last example, so why not? Let's do this. All right, so we've got lambda minus 2, negative 2 and 2, negative 2, lambda plus 1, and negative 4, 2, negative 4, lambda plus 1. Okay. So again, I'm just going to start here with lambda minus 2. In this case, it really doesn't matter which row or column we pick. Again, there's no zeros, so there's no shortcuts to this process. Lambda minus 2 times the determinant of the kind of the lower right corner. We're going to have lambda plus 1 times lambda plus 1, or lambda plus 1 squared, minus 16. And then I'm just going to go across. So remember, we have to do minus a negative 2, so that's really a plus 2. And then we'll have negative 2 times x, or lambda plus 1. And then minus a negative 8 is plus 8. And then going across the last 2, that's a plus, so plus 2. Negative 2 times negative 4 is 8, minus 2 times lambda plus 1. All right. So now we need to kind of simplify this down to standard form so we can actually get our eigenvalues. So let's just kind of take care of some of the stuff in the brackets. So we've got lambda minus 2. Expanding out gives us lambda squared plus 2 lambda. Plus 1 minus 16 is minus 15. And then plus, the inside of this is going to be negative 2 lambda. Minus 2 plus 8 is a plus 6. And then we're going to multiply that by 2. So actually this is going to be a minus 4 lambda plus 12. And then for the last set of brackets, that's going to be 8 minus 2 is 6, and a minus 2 lambda. And then multiplying through by 2, we'll have a plus 12 minus 4 lambda. All right. So multiplying out, I'm going to actually multiply this whole thing out now. So multiplying the binomial by the trinomial gives us lambda cubed. We'll have a 2 lambda squared minus a 2 lambda squared, so those cancel. We'll have a negative 4 lambda, and a negative 15 lambda is negative 19 lambda. That's a 19. And then plus 30. And then we've got, on the outside, we've got a negative 4 lambda, and a negative 4 lambda is negative 8 lambda, plus 24. All right, so that is lambda cubed minus 27 lambda plus 54. All right. So this, again, is one of those where I wouldn't bother trying to factor this. Just go ahead and graph it. And when you graph it, you're going to find the zeros. Now, in this case, when you do graph it, what you're going to get is a graph that looks something like this. It goes through at -6 and then touches at 3. Now, if you remember, I don't want to make any assumptions here. When a graph passes through, you have an odd multiplicity, usually 1, but it could be others. When it touches like this and kind of bounces off the axis, you have multiplicity that is even. Now, in this case, because it's a cubic function, we know that we have 3 total zeros, real and non-real together. So if it touches 3, that tells me that there's 2, that it has multiplicity 2 at 3 and multiplicity 1 at -6, and that's going to give us our 3 zeros. So that tells me that this factors x plus 6 and x minus 3 squared, giving us our eigenvalues of lambda 1 equaling -6 with multiplicity 1, and lambda 2 equaling 3 with multiplicity of 2. Okay, so we've got our eigenvalues. So that was the first part, right? So number 1 is done. Find all the eigenvalues of A and determine the multiplicity of each. Now we have to find for each eigenvalue of multiplicity 1, we're going to find a unit eigenvector. Okay? So it doesn't matter what we find. Once we get it, we're going to normalize it anyway into a unit vector. So for lambda 1 equaling 6, we're going to go through the process of finding its eigenvector. So negative, that should be a negative, not a positive. Eraser would be good. There we go. So that should be a -6. So we've got -6i minus a. And that's going to give us the matrix -8, -2, 2, and then -2, -5, -4, and 2, -4, -5. Matrix, not determinant. Again, we want to row reduce these all the way. So again, just use technology to do this. 1, 0, -1/2. 0, 1, 1, and 0, 0, 0. So in this case, we have x1 minus 1/2 x3 equals 0, and x2 plus x3 equals 0. So I'm going to let x3 be t, which means that x1 has to be 1/2 t, and x2 has to be -t. So x1 is going to be, x1 was 1/2 t, x2 is -t, x3 is +t. Now, if you want to, you can multiply everything by 2 to get rid of that fraction, which I'm going to do. I'm going to write this as 2t t, right? Multiplying by 2 is t, -2t and 2t. It doesn't matter because, again, we're going to normalize this anyway, but I don't want to deal with the fraction when I'm having to normalize and do the square root and everything. So this will just make some of the work a little bit easier. But what that tells me then is we've got a vector, an eigenvector of 1, -2, and 2. Okay? Now we need to normalize that. So if you remember, to normalize this, we're going to basically create a new vector by taking v1 and dividing it by the magnitude of v1. That's going to create a vector of length 1. It's going to create that unit vector. So the magnitude is really just the length. It's the square root of 1, or it's 1 squared plus -2 squared plus 2 squared. So we just square each of the components, add them together, take the square root. And that's going to give us, 1 plus 4 is 9. Square root of 9 is 3. So we'll have 1 over 3 times 1, -2, 2. And that gives us the vector 1/3, -2/3, and 2/3. So this is the normalized eigenvector for lambda that had a multiplicity of 1. So that basically takes care of step 2. Now we're going to do the same thing for anything that has multiplicity greater than 1. The problem is that when we find these eigenvectors, they're not always in an orthonormal set. They're not always orthogonal and certainly not often unit vectors. So we're going to have to do both. Once we get these vectors, we're going to have to go through the process of making them orthogonal and then normalizing them. Okay, and that's where some of the heavy work comes in on this. So, not that we haven't done a lot already, but so for lambda 2 equaling 3, again we're going to go through the process of finding its eigenvectors just like we always do. So we're going to start with that normal process. So again, plugging in 3 is going to give us 1, -2, 2. And then we'd have a -2, 4, -4. And then we'd have a 2, -4, and 4. Or excuse me, 2, -4, and 2, -4, and 4. All right. Again, Gauss-Jordan elimination, row reduced. We get 1, -2, 2, and then the rest are zeros. So in this case, we'd have x1 minus 2x2 plus 2x3 equals 0. So I'm going to let x2 be s and x3 be t, which means that x1 would have to be 2s minus 2t. So x2 is going to be 2s minus 2t, s and t, which if we break that up into its linear combination is going to be, and I'm going to pull the s out just so we can really see the vectors. We'll have a 2, a 1, and a 0, and then plus t times a -2, a 0, and a 1. So we have 2 eigenvectors here, which we'd expect because the multiplicity is 2. And that gives us a vector of 2, 1, 0, and another vector -2, 0, 1. Now, a quick check to see if these are orthogonal. We just take the dot product, and we'd have a -4 plus 0 plus 0 is clearly not 0. They are not orthogonal, unfortunately. If they were, we could actually just normalize them and be done. But they're not orthogonal. So V2 and V3 are not orthogonal. And because they are not orthogonal, we have to use the Gram-Schmidt process. Now, you might be asking, Gram-Schmidt, that sounds kind of familiar. And Gram-Schmidt process was something that we did back in section 5.3. So if you need to go back to that section, either in the video or in the book, brush up on it, feel free to do that. It'll start to come back. You will not have these formulas memorized, so you'd probably have to go back and look at them anyway. But I think as soon as we start, you're going to go, oh, I remember doing that. So let's start with V2. And this is where we say that W2 equals V2, which is just going to be 2, 1, 0. And then W3 is going to equal V3, which we find, or excuse me, is equal to V3 minus the quantity dot product of V3 and W2 divided by the dot product of W2 and W2. And then that is multiplied by the vector W2. So this probably hopefully looks familiar. But obviously I highly doubt you've got those formulas memorized. If you do, you are amazing. All right, so V3 is -2, 0, 1. This whole dot product, the dot product of V3 and W2, I'm just going to give this to you. I calculated this earlier, is basically this whole thing is negative 4/5. So we'd have a negative 4/5 and then times 210, the W2. Okay. And if we calculate that out, we will get the vector negative 2/5, 4/5, and 1. Okay. Let's draw that a little cleaner. There we go. All right, so now we have W2 and W3. And if you check those, and I encourage you to do this, but if you check those, you'll notice that the dot product is 0. That tells us that these two things are orthogonal. Okay, so that condition is met. They're orthogonal. Now we just need to normalize them. So now we're going to normalize W2 and W3. And let's call those then U2 and U3. So U2, normalizing, we're just going to take W2 divided by the magnitude of W2. So the magnitude of W2 is the square root of 5. So I'm going to write this as 1 over the square root of 5 times 210. And that's going to give us 2 over the square root of 5, 1 over the square root of 5, and 0. And then for U3, we'll take W3 and divide that by its magnitude. So the magnitude of W3, oh boy, let's see here. We've got 4/25. I'm going to write this out. 4/25 plus 16/25. If I make 1 5 over 5, that's going to be 25/25. So that is 41/45/25. Now remember, we're dividing by this. I like to show it as multiplication, so I'm going to flip it. We have to take the square root of this. And so that's basically 5 over root 45, which is 3 root 5. So this is 5 over 3 root 5 times negative 2/5, that's a 5, 4/5, and 1, which is going to be, the 5's cancel, negative 2 over 3 root 5. Again, the 5's cancel, 4 over 3 root 5, and 5 over 3 root 5. Okay, so let's pause and just go back and just what did we do here again? So we were going through, we found the two vectors, the eigenvectors for lambda 3, or for lambda 2, which was 3. But again, these vectors v1 and v2 are not part of the orthonormal set. They are neither orthogonal, nor were they unit vectors. So first thing we had to do was transform them into orthogonal vectors using the Gram-Schmidt process. Then we had to normalize them. So these two vectors are both orthogonal to each other, and they are unit vectors. So they form an orthonormal set. So now we have three vectors. We have the one that we found up here, U1. We've got these two down here, U2 and U3. So what we've done now, we just finished step 3. That was a big step. And now step 4 says, taking all of those vectors that we found, we're going to use them to create the columns of P. And P is the matrix that orthogonally diagonalizes A. So finally, in step 4, P is the matrix 1/3, negative 2/3, 2/3. Remember, these are column vectors. And then the two that we just found, 2 over the root 5, 1 over root 5, and 0. And then negative 2 over 3 root 5, 4 over 3 root 5, and 5 over 3 root 5. So that is the matrix that we're looking for. That is P. Okay. Now, that's it. But if we wanted to kind of verify, if I take P inverse times A times P, that should give me the same thing as if I took P, P transpose times A times P. And it should give me a diagonal matrix. So again, use technology here to verify this, but if you multiply those together, you should get the diagonal matrix negative 6, 0, 0, 0, 3, 0, and 0, 0, 3. Wow, that was a lot. That wraps up this last lesson. That wraps up all of our lessons for this class. We are not done yet. Obviously, you've got more work to do. But wow, thanks for hanging in there. Thanks for watching all of these. And there's no more lesson to see you in next. You take care.